Okay, in this video, we're going to look at something called the limit comparison test. And in the last video, we looked at the direct comparison test, and we'll take a look at both of these and see what they have in common and what they have different. First of all, the limit comparison test, if you look in your book, here's what the rule looks like. It says if you have two sequences, A and B, and they're both positive, that the ratio of those two sequences as n goes off to infinity, if it's equal to a constant, then you can show that the two series either both converge together or both diverge together. Now, in this form, it's kind of hard to picture what's going on, so let's take a look at both the direct comparison test and the limit comparison test side by side and see what they look like. So again, this is the one in the last video we looked at direct comparison test, and they have some things in common, they have some things different. So direct comparison on this side, limit comparison on this side. Now, first of all, let's talk about what things do they have in common. So the ideas on both of them, they start the same. Let's first of all look at a case where they converge. So you have convergence. So in both cases, you've got an original one. So this would be the original series or sequence here. And then over here, you've also got an original sequence. So in both cases, you start out with an original sequence. Then the next step in both cases is to do this. You've got a complicated original sequence. So you would like to compare that to hopefully a simpler test sequence. So we'll call this the test sequence. And in both cases, that'll be the test sequence. So we'll come up with a new sequence to compare it to. Now the idea is if the test sequence is a little bit simpler, you will know whether the test sequence diverges or converges. And then you can use that information, the behavior of the test sequence, to predict the behavior of the original sequence. So in this case, let's first of all look at the direct comparison test, and you should be familiar with this one by the last video. Now suppose we're going to look at a case where it converges. So let's take a look at the graph down here. If it converged, then the test sequence would look something like this. If you were to take this B series and plot them, if the test sequence converges, then that means that the dots have to be approaching the x-axis at a good enough rate, and a converging sequence would look like this. Now over here, we'll do exactly the same thing, exactly the same points. You've got another test sequence, and it approaches the x-axis. This is what it would look like. So you know that both of your test sequences are converging. So at this point, both the direct comparison test and the limit comparison test start out exactly the same way. But now to determine whether the original sequence converges or not, they use two totally different approaches. First of all, let's look at the direct one. So this one says that if the test series converges, then you can show that the original series converges if the original series is less than the test series at every point. Now what that means is this, is here's your test series. You have to be able to show, and I'll put some dots in here just a second. If this is the original series, then the original series has to be below the test series at every point in the sequence. And if you can show this is true, that the original series is less than the test series, then that means that this original series converges. Now you might also remember from the direct comparison test, if the original series is below the test series, you show that it converges. But if you had this case, suppose the original series was above the test series at every point. Suppose it did this. Then in this case, it doesn't satisfy the requirements of the rule, so in this case, the test failed. So if the original series is above the test series, then the test fails. If the original series is below the test series, then you show that it converges. This one, in this case, it would, if it's below, it converges. So it's all based on the fact of is the original series less than or greater than the test series? Now what the limit comparison test does, it starts out the same. You've got a test series, but it follows a completely different approach. And it says this, if you've got the two series, if you take the ratio of the two series, and that ratio is equal to a constant, then you can show that both of them either converge or diverge together. Now in this case, we already know that this one converges, so the test series converges. Now what does this mean? And actually you can write it like this. You can put either the original over the test or the test over the original. So in this case, let's do this. Let's put the original over the test series. And let's just assume, just to give it a number, suppose it turned out to be 1/3. Now what does this mean? If the limit of the original over the test series turns out to be a constant, if L turns out to be a finite positive number, then you've showed that since the test series converges, that the original series converge too. But graphically, what does it look like? Well, what this means is that the original series will always be, and if it looks like this, you can move the test over here. That means that the original series will always be 1/3 of the test series. So what that means is whatever this blue height is, the red height will be 1/3 of it. So if you go way off to infinity, now it may not be exactly true close to 0, but the farther you get to infinity, it'll settle along a pattern where if this height is the test, 1/3 of that height is the original. If this height is the test height, then the original height would be 1/3 of it. If this height is the test height, then the original height would be 1/3 of that. That's the test height, so the original height is 1/3. That's the test height, the original height is 1/3. So each point in the original sequence will turn out to be 1/3 as tall as this one here, and that's what this means. So if the ratio is 1/3, it means that the original sequence is always 1/3 of the test sequence. And the way this rule reads is this: if you have a sequence that you know is converging, if there's another sequence that maintains the same height ratio, then that second sequence must also converge. They may not be getting down to the x-axis at the same rate, but eventually they'll both get there. So again, if the first sequence converges and the second sequence maintains the same height ratio, then both sequences eventually have to converge. Now, the limit comparison test has one other advantage over this one, and this is this. This test only works if the original sequence stayed below the test sequence. What this one does, it works whether it's below or above. And let's take a look at it. Again, you can put either one on top. Suppose you did this. Suppose you put the test sequence on top over the original sequence. And suppose, again, it turned out to be 1/3. Well, if you move the 3 over here and the original over here, this means that the 3 times the test sequence would be equal to the original sequence. So this means that in this case now, if you put this on the top, the original sequence is always 3 times the test sequence. So in this case, it would look like this. Suppose you had this right here. This is the test sequence. So the original sequence will be 3 times as high. It'll be up about right here. This is the test sequence height. So go 3 times as high. It'd be about right here. Here's the test sequence. Go up 3 times as high. It'd be about right here. Here's a test sequence. Go up 3 times as high. It'd be about right here. There's the test height. Go up 3 times as high. You're about right here. There's the test height. Go up 3 times as high. You're about right here. The test height 3 times as high. You're about right here, and so on. Now notice, what this does is, in this case, the original sequence is above the test sequence, but the rule still applies. It doesn't make any difference whether it's above or below. If the blue sequence converges and the red sequence matches the height ratio of the blue sequence at every point, then the red sequence also must converge. And you can tell it by looking at it. It doesn't make any difference whether it's above or below. So as long as they maintain the same height ratio, eventually, if the blue one converges, the red one's going to converge. Now that's what it looks like if they converge. It'll be sort of the same logic if they diverge. Let's take a quick look at that. Okay, now, same situation, but the only difference is this time the test sequence diverges in both cases. Well, what the direct comparison test says is that if you know that the test sequence diverges, the original sequence can only diverge if it's greater than the test sequence. So it might look something, say, like this. The test sequence or the original sequence has to be above, and if that's the case, then it diverges. But if the original sequence happens to turn out to be below the test sequence, then again, the test fails and you can draw no conclusion. So the test fails. So if you're checking for divergence, this is the original right here. The original series has to be above the test series. Now again, kind of the same situation over here. Let's just give it numbers. Let's suppose we had the original one again, and you're trying to find a ratio. So you can do either original over the test or the test over the original. But suppose we had this. Let's suppose that we did a test, and when you found this limit, it turned out to be 2, which is 2 over 1. So what this means is, now you know that the test series diverges, so it's going to diverge, and if the original series, now if you were to plot it, here's what it would look like. That's the height of the test series. The original series would be twice as high. Take this height, double it, and you'd have this. Take this height, double it, and you'd have this. This height, double it. So the height of the original series, as you go way off to infinity, is going to be twice, might look something kind of like this. But your claim is still this. If the blue series diverges and the red series maintains a constant height ratio to the blue series, then the red series must also diverge. So they either converge together or diverge together. Now again, it doesn't make a difference whether it's above or below. If you were to switch this and put the test, suppose you decide to put the test on top of the original. And suppose, again, you got a 2 for 1. Then that means whatever, if the test one is a height of 2, the original one is a height of 1. In this case, each one of these would be 1/2. So if you did this one, each red dot would be half as high as each blue dot. But again, they'll maintain the same ratio. But again, this thing still diverges. So it doesn't make any difference which one's on top. If the blue one diverges and either one of these two red ones maintain the same height ratio, whether it's 2 or 1/2, depending on what you've got, they both diverge. So that's just a brief introduction to the difference between the direct comparison test and the limit comparison test. They have some things in common and some things not in common. And what we'll do in the next thing here, we're going to look at a sample problem, and we'll work at using both of them and see what that looks like. So we'll turn this off, and I'm going to turn this back on just for a moment. And let's look at a problem. Okay, so the problem looks like this. We're going to work exactly the same problem in both cases. I want to find, does this series converge or diverge? And this is exactly the same one. Let's first of all try it with the direct method, and we'll kind of do the steps at the same time. Now, the idea is in both cases, you've got an original. So here I have an original, and over here I have an original sequence. So I want to find a test sequence that behaves similar to this thing. And if you watch the previous videos, look at the dominant term. N squared is the dominant term. If you go way off to the right, this -4 basically disappears, and you will be left with 1/4, or pardon me, 1 over n squared, and that's going to be your test sequence. So you're trying to find a test sequence that models the original sequence. So here's the test sequence. Now, you do the same thing over here. We want to find a test sequence here, and we just found a test sequence here. So in both cases, find a test sequence. Now this one will be the same thing. If you go way off to the right, that 4 becomes insignificant, and this thing behaves as if it was a test sequence of 1 over n squared. So now the next question is you have to decide, does the test sequence converge or diverge? Well, looking at this is a p-series test with p equal to 2. And again, if p is greater than 1, then this thing is going to converge. So you know that the test series converges. This one is exactly the same thing. So you need to figure out, does this test sequence converge or diverge? Well, same argument. It's a p-series, exactly the same thing. So it's a p-series with p equal to 2, which implies, again, that this test series, actually test sequence, converges. And if you took the limit, if you're doing a p-series, this would actually be a summation here and a summation here. So you're actually showing that the series that results from that sequence converges. But anyway, at this point, both these two processes are exactly the same. So you started with an original, you found a test sequence, and you figured out what's going on with that test sequence. It converges or diverges. Now here's where they're different. Let's finish it up and see what we can do with this one. Now that you know the test sequence converges, you want to know, does the original sequence converge? Well, the original sequence will converge if the original sequence is less than the test sequence at every point. So if you're following the direct comparison method, your next step would be to take and say, does the original sequence, is that less than the test sequence? Because remember, if it converges, it has to be less than. So the original sequence is 1 over n squared minus 4, and you're going to compare that to 1 over n squared. Now, if this turns out to be true, that means you satisfied the direct comparison test and the original sequence converges. So now apply some logic. If you take any number here and square it, this number, you've got the denominator on this side is n squared, the denominator on this side is n squared minus 4. So whatever number you get here, this number right here is going to be a little bit smaller. It'll always be 4 less. So this denominator here is going to be less than this denominator here. Now, if the denominator in a fraction is less, that means the entire fraction is greater. So what you've really got here is this situation. I'm going to put a question mark. I wanted to know is this true or not? So is this true? And it actually turns out n squared minus 4, because this denominator is always smaller, the fraction will actually be greater than 1 over n squared. So on this case right here, the original is greater than the test case. And that's what you showed. So what this means is, since the original is greater than the test case, let's go back and look at our original thing up here. Remember, it's this series right. The blue dots represented the test case. You've just showed that you have these red dots up here. The red dots are greater than the blue dots, therefore the test fails and you can draw no conclusion from this. So we go back here. This means that the direct comparison test fails and you can't conclude anything. So that's what happens if you try to solve this problem with the direct comparison test. Let's switch over to the limit comparison test and see what happens over here. The first few steps were exactly the same. At this point, you know that the test series converges. Here you knew the test series converged. But now, rather than doing this step and showing that the original, and trying to show at least that the original sequence is less than the test sequence, in this one, you're going to do this step right here. You're going to try to show that the ratio of the two sequences is a constant. So you'll take the limit as n approaches infinity of, now again, you can put the original over the test or the test over the original. I like to think of it like this. I'm just going to put the original over the test. And I want to know, is it a constant or not? So what that's going to give me would be the limit as n approaches infinity, and the original function is 1 over n squared minus 4, and I'm going to divide that by, I'm going to move it way down here, 1 over n squared. So it's going to be this sequence over this sequence. Now again, you got a fraction divided by a fraction, so the first thing to do would be to invert and multiply. So we'll take the limit as n approaches infinity and make this be 1 over n squared minus 4, and take the reciprocal of the denominator, n squared over 1. Well, what this gives you is the limit as n approaches infinity of n squared over n squared minus 4. Now, if you were to take the limit of this, and just a reminder, it's a rational function. You've got a polynomial on the top, polynomial on the bottom. The power in the top is the same as the power in the bottom, so the limit is just the ratio of the leading coefficients of that thing. So it'll be 1 over 1 or 1. Now what you showed is this is L. The ratio of these things is 1, and 1 has to be a finite positive number. If it's a finite positive number, then that means, you look up here, that since it's equal to a number, that both series either converge together or diverge together. Well, since the test series converged, then you can conclude that the original series has to do the same thing. So here you can conclude that the original series also converges. So again, if the test series converges, then, and the ratio is a constant, then the original series converges. So the direct comparison test for this problem failed because you couldn't show that the original series was less than the test series. But on this one, when you use the ratio was a constant. So whatever the first sequence is doing, the second sequence is doing the same thing. So since the test series converge, the original series converge. So both of them kind of have their strengths and advantages, but that's just an example of, in some cases, the limit comparison test might be able to solve a problem that the direct comparison test can't. So anyway, that's just an introduction to the limit comparison test.